Hello, y'all. Darrell Berry Jr. back as promised with some quantum mechanics today. Uh, so Catherine had asked about a magnetic field, how it affects a subatomic particle on my other channel, where I'll go a bit more in depth on my STEM channel a lot of times. And I said I'll make a show about that, regular show, bit more in depth topic. But I think it should be interesting. And fair warning, this is like stuff at the edge of my understanding of things. So I may get something wrong here or there, definitely. But I try to go slow and uh, see if I can get everything as right as possible, of course. And what I'll do is basically start by talking about what the Zeeman effect is in general, and giving like a up front, give like a what it actually is. And then I'll go into some detail about some background of how we get these states that are going to split apart. Now, I'm pretty sure I won't be able to finish everything today, so I set a part two for tomorrow evening. So the plan is to come back tomorrow and finish the next half of it. So that'll be the plan. So I'm basically going to be drowning in thermodynamics and quantum mechanics for the next week and a half. So my final for thermal is next week, and my final for quantum is on the 5th. And I'm supposed to be meeting with one of my classmates tomorrow to go over the thermal homework, the last homework that's due on Wednesday. So that should be cool. And it's awesome. So we'll go ahead and jump in. As you all show up, be sure to like, subscribe. I do notice every time I start, there seems to be some kind of keyframe thing going on. Uh, saying set keyframe. Why don't y'all let me know? It doesn't. I don't seem to see any um, issues with the stream. And for some reason, I always get this error every time I start. Uh, but I'm still on this stuff. So if somebody has any tips on the keyframe thing it's talking about, maybe it's that. Let's see if that does something. I don't know. Okay, let's go. Let's see what we have going on. All right. So let me bring up the textbook, and we'll get to that momentarily. That's a cup scoring table. So I try to get the page to show directly in the middle, but it's kind of hard to get that to happen. So it says the Zeeman effect. When an atom is placed in a uniform external magnetic field, be external, the energy levels are shifted. This phenomenon is known as the Zeeman effect. For a single electron, the perturbation is that equation there. H should be the operator that allows you to get the energy for a function. The Hamiltonian, it's like an altered Hamiltonian because there's a parentheses or a prime and a z next to it, which should be for the Zeeman effect. So basically, it is the Zeeman Hamiltonian. It's like we have the magnetic L, the magnetic S, dotted with the external field, so we can see how the um, are you all seeing? Let me elevate the book a bit. Yeah, that it better. So you can see the equation there. It's basically a Hamiltonian for the Zeeman effect, negative magnetic L quantum number, magnetic S for the B external field. You know, a lot of that doesn't make sense to most people who haven't studied this. It still makes only so much sense to me. I'm in quantum 2. So we'll go ahead and go through what this means. And but the general idea is that we can have uh, states of atoms and subatomic particles that have the same energy. We call these degenerate states. So you might have several different ways for particle to have energy at the same level. So these states are sort of stacked on top of each other. But what happens is if we were to take an external magnetic field and run it through the particle, even though these states have the same overall energy, the particular configuration of the particles are different. Therefore, they respond differently to the magnetic field. So what ends up happening is where at first you had a bunch of magnetic um, particles that have the same exact energy, now you have splitting of these energy states, where the magnetic field is causing the slight differences in the configuration of the little bitty pieces of these particles to behave in different ways, and I'll talk a bit about what those pieces are. This is basically the Zeeman effect. The professor actually went over a few of the ways that these things are practical in life, which I don't actually recall. But basically, what happens is there's technology that we have that only operate because these particular states can be activated or be differentiated in magnetic fields. And something that comes to mind, it might have something to do with like MRIs. Like I don't even know MRI. We get into a magnetic field, and it actually polarizes the protons, the subatomic particles in your body. Either the protons, the electrons. I think the protons. And because different densities of material will respond differently to the magnetic field, the stiffness of the charges will, spin more or less depending on the material. Thus, bones show up differently than flesh shows up differently. So, I believe it has something to do with that. But I don't remember specifically the technologies, but it's part of our everyday lives to a certain extent, whether we realize it or not. So, the key background to understanding this is understanding the degenerate states themselves and seeing what they are, and then we can calculate the energies of these degenerate states when they're affected by a magnetic field. So some of the magnetic uh, or subatomic components we'll talk about is the N number, and this is the principal quantum number. So the N number basically tells us the energy of the state of the particle. So N is going to be greater than or equal to 1. And if you've been following me for a while, you probably recall us doing like harmonic oscillator energies and uh, uh, particle and the infinite well energies. And you might have something like E equals uh, H bar omega n plus 1/2. So this would give us the energy state of a harmonic oscillating subatomic particle given the value of n. Or we had a particle in a well, it would be something like En equals, let me see if I can recall it, n squared pi squared h bar squared over 2m a squared. So if you have a particle in a well, which can be in practice, you start doing this with a mock well, like you imagine you have some kind of potential here that's very low, and your particle is sort of trapped in this well, and you calculate the energies. And in real life, what happens is you have a proton, like for instance in a hydrogen atom, and you have basically an electron that has to deal with this proton being there and the Coulomb attraction that it feels for that proton. And that ends up being a role in real life, which gets to be pretty complicated. So you start with simpler configurations, but that's the N. The N is going to tell you the energy of the state that you're working with based upon whatever N level you're dealing with. We'll talk about L and M. So L number and N number deals with angular momentum of the subatomic particles. So when we talk about L, we're talking about the azimuthal angular momentum. And this is basically the shape of the the shape that the electron will make around the atom. So for instance, if L equals 0, if you look at a periodic table, this will be the S part of the periodic table. And it has sort of a spherical shape. So it's kind of like the electron field has a shape, sort of a cloud, a spherical cloud around the nucleus. If L equals 1, this will be the p orbital. So if you look at a periodic table, the p orbital, every element in a p orbital is in an L equals 1 state. And this orbital sort of looks like these clouds that look like this. So it's kind of like these bulges that come out around the nucleus. The nucleus would be up in here, and these things are sort of like this. And it actually is quite relevant, like when you get into chemistry, because it determines how the molecules are actually shaped. So if you, for instance, have four of these things, if you have two, like for instance, L's together, and I'm just may not be precisely how it is, but if you have four of these things, they're going to be repelling each other because these are electron fields. So you might end up with something like this, like a tripod shape, because they'll be repelling each other, and the negatively charged electrons won't want to get too close to each other. So they're going to want to maximize their distance. And there's other things that play as well, which you might end up with. I don't remember the exact angle it'll be, but 108 degrees or something like that, all the way around here. I don't remember the exact angle, but you see my point. So um, these things are quite relevant when it comes to the actual mechanics of how molecules form, the way they look, the way they're shaped. If L equals 2, this will be the D state in the um, periodic table. And these basically have four lobes, looking something like this. So it gets a bit more complicated. Uh, Things like with this kind of configuration, you might have a molecule that looks like this, and you have a lobe coming up and down, so you can see it's sort of maximized where everything is as far as away from each other as possible. We have a lobe, these four lobes like this, and these two poking out, and it makes this symmetry given the pull and push and pull of the Coulomb forces. And if L equals 3, then we're dealing with an F state, and you basically have 8 lobes. It's kind of like 4 front, and then there's 4 sort of behind these still spread out so that they maximize their distance from each other. And these are basically the L numbers that we're working with. Um, we also have ML. So ML numbers are the magnetic quantum number. this M here, and pretty much every quantum number, I guess except N, has its L, that is basically the orientation of the uh, orbital in space. So it might tell us which orientation these lobes have, for instance. Then, which we'll have to deal with, which we spoke about before, is an inherent property of some atomic particles. And it's not like spin around in a circle, uh, but it's an inherent property of, let's say, electrons, where electrons have a uh, 1/2 spin. Lisa says, is there an upper limit to L? Uh, I don't think so. I guess the limit is just how many particles we found. So when we look at the periodic table, off the top of my head, it looks, you're familiar with it in general, how it looks. And then there's like a part that's cut out here and it's like long like this. And if I recall, this will be the S, this will be the P, this will be the D, and this will be the F. But my understanding is it may go above that. I'm not a pro on this part. Off the top of my head, if you look at a periodic table, these are the areas that we're looking at. And this is the part that's stuck out. So technically, as many, I guess it has to do with how many electrons are at play. The more electrons you have in the particle or the atom, the more complicated it gets, the more they have to maneuver themselves, and you end up having more and more orbitals for them to fit. But it's just that I'm still an undergraduate, so, and I can't say I particularly am enamored by quantum mechanics. I mean, I have to take it. Every physicist have to take it and understand at least a minimum amount. And it's understandable why, like, I like astronomy, and pretty much you deal with a lot of quantum stuff, analyzing light. It's coming from the electrons, and we have to know a little bit about it, but pretty sure the chemistry majors will really know about that. In physics, for so far, all we've dealt with is S, P, D, and F, and we rarely actually deal with D and F. We mostly deal with S and P, and a little bit of I don't think we ever did a problem actually with F. Good question, Lisa. Thanks for the question. Thanks for dropping a line. And anybody else as well, if you have any questions or comments, I'll be checking the chat. Make an extra space here. Maybe I'll make an extra few spaces. So this spin is inherent. And the way they discovered this, by the way, is back in the day when they were doing everything by hand. Amazingly, I'm still amazed by that. What happened is a experimenter whose name I probably should remember. The professor actually asked stuff like that on the exam for bonus questions. But suffice it to say, he created a device where he can send electrons through a magnetic field, a stream of electrons. And what he noticed was that given the strength of the magnetic field and what he did, he was able to confirm the splitting of the states to a certain degree. But he noticed that he was only getting two streams. So if a particle has a spin 1, you end up getting three streams, where there's two going up and one going in. I don't know the details of exactly why, but the professor talked about it, but you know how it is. You don't catch everything. When they did this experiment with electrons, he figured out a way to do it. Uh, he noticed that they were only getting two streams, and then we knew and understood that an electron is a 1/2 spin, because the spin is basically conserved. So you end up getting so many one up and so many down, and basically it's going to serve so that you get basically the roughly the equal half of each of those. I guess if you had an infinite number of electrons to send, it'll be perfect. But of course, we don't have an infinite number, so we get a rough average. And each of the spins have their ms as well. Like I said, about every quantum number has their m. So that's basically the magnetic quantum number of spin. And the last thing we'll talk about that actually there's three more things. Okay, it gets complicated. The last technically four quantum numbers we'll talk about is there's the L number, and this is the total uh, orbital angular momentum. So what ends up happening is when you, let's say, put a proton and an electron together, the proton has its spin, the electron has its spin, they have their angular momentum, and they impact each other. Just like how you have two magnets. I'm sure everybody has taken two magnets and put them close to each other. You know, if you put the two same charged sides next to each other, you could feel them repelling. If you put the opposites, they attract. Well, that's going on with the proton and electron. Their magnetic moments are affecting each other. And these magnetic moments have a particular a combination. So L is basically the total of that, uh, the total orbital angular momentum. And S, and by the way, this is by vector addition. And S, capital S, is the total spin angular momentum. So basically, all the spins you add them up. You know, the spins of all the different particles, all the L's you add them up. All of these different particles have their own L's, their own S's, and all of that stuff. They're coming later. No mistake. And also, there's the J, which is the L plus the S. And you can also have the lowercase. So what ends up happening is when you combine these particles, the J is the total angular momentum. So this was the L was the total orbital angular momentum. Remember the uh, uh, angular momentum is basically the orientation of the the clouds, and you sort of have the total angular momentum all together, and that takes the L and the S together, and this is what ultimately we end up working with to get the degeneracies. You have the J, and you have the MJ, so the sub number of those J's. And this is like the grand number that takes all of these things together. You have your L's added together, your S's added together, then you combine those, and you sort of get the net effect on the particle, right? So you kind of say that all of these things are combining together, and J sort of ends up giving us the overall effect of what's going on with that particle. And we get the MJs of the J's, and then we have our degeneracy. So now that was a lot. So what I'm going to do is to close out, you know what I'm saying, close out now because it'll probably take the rest of the time. I'll actually show you how this works for an N2 particle. So I worked on it before, and after that, I asked my professor for some clarifications on some things. But I'm certain I have it worked out enough to get through it now so that you understand it at least basically how this works and how we map, you can say, a subatomic particle. So let's say that we have hydrogen, and let's say we have hydrogen, a total atom of the n equals 2 state. So in other words, n is going into the energy to give us the energy of the particle. So this is the primary number that's going to let us know what everything else is going to be. Because everything is going to happen according to how much energy is there. If there's not enough energy to excite the electron, it is not going to behave at that level. So it all starts with the N. And from there, it works like this. So after you have N, the L that corresponds to that N is going to go from 0 to 1 to 2 on up to N minus 1. So L would be every number from 0 up into 1 minus 1 less than the N number. So if my N equals 2, the L's that I have available to me are going to be 0 and are going to be 1. These are the L levels that are available to a particle that has N amount of energy when you plug that N into whatever type of environment you're looking at, whether it's a harmonic oscillating particle or a particle in the well, you input that in, it gives you the type of energy. That amount of energy would allow you to have either a s orbital or a p orbital. Right? So it's a little bit of energy for the small atoms that we small energy levels. Right. So once you have your L, then your ML is going to be the negative L on up through the positive L. You're gonna take all of your L's and go from negative to positive of what they are. The tricky part is you have to do it for each L. What I mean by that is L equals 0. So ML for L equals 0 is 0. L equals 1. So ML for L equals 1 is going to be negative 1, 0, and 1. And you can see how it can get complicated the more complex the molecules or atoms you're dealing with, the more L levels there are. Because again, uh, when this orbital fills up, the electron doesn't have any more room. Then it needs to go out to the bigger one. Well, eventually these lobes fill up. Then you start having this lobes, and then these lobes fill up, so this starts looking like this. So it gets more and more complicated. The more and more electrons are packed into, you know, a grouping of protons and neutrons, which is the nucleus of the atom. But again, we start by dealing with these smaller ones because it gets more complicated as you get more and more advanced. My well, I guess technically he's not my professor. I work with him. I'm the class I'm a learning assistant in. Yesterday was it? No, Thursday. We were sitting, hoping to finish up the grades for the class, and we both of us got there early, so we were just talking, and he was telling me about uh, back before we had computers and everything when he was in school, and even before him, there was a guy who calculated all the states for, I believe it was, I forget the exact molecule atom it was, but it was an atom with like 30 something electrons. And he said it took him like a year to calculate all the states by hand, like to calculate all the entities and how everything goes. It took him like a year, but he did it. And what he told me was later, the professor was telling me this, he said later what he did was, now that we have computers and stuff, he actually programmed the code to calculate the states for that atom, and he got the exact same answer that guy got like 100 years ago by hand. It's amazing. I'm always amazed. I mean, yeah, OMG is right. I mean, dude, the fact that we have the technology we have is because of what those people did. I mean, what they did is amazing. All right. So those are our L values. All right. And then, so let me scroll to the proper part of my notes. There we go. So I got my L's right. Okay. So the last thing we'll look at are the J's. So, so as we said before, the J is like the big kahuna. The J is when you finally get to the end like we did. We got our N's, we got our L's. Now we're going to combine our L's and our S's, because now, we're putting these particles together. They have their own L's, their own S's. What's going to be the end result? And the way the J's work is by adding, as we said, the L's plus or minus the S's, but it must always be greater than 0. So the J will be L plus or minus S, but greater than 0. So let's see how that goes. So let's say I have, let me make sure I look at, so there we go. So we have L equals 0 here. Actually, let me back up. So we have N equals 2. L equals 0. So ML equals 0. Just rewriting what we have there just to keep it straight for myself, really. So we have J equals L plus 1 over 2, because again, we're dealing with electrons, and maybe I didn't make that clear. We're dealing with a hydrogen atom. You basically have a proton and an electron, basically. You're dealing with the spin is going to always be 1/2 because the electron is sort of the operative agent here, the thing that's going to leave or go away or come back or move levels. So this is going to be 0 plus 1/2. So we have 1/2. So J equals 1/2 for L equals 0. And if we do J equals L minus 1/2, it's going to be 0 minus 1/2, negative 1/2, but we said it has to be greater than 0, so that doesn't work. So that means that for the N2 state, with L equals 0, ML equals 0, we only have the J of 1/2. So I'm going to go ahead and remove some of this. I just wanted to make sure I wrote it out so y'all can see what's going on. So I could give myself some room. Now we know why we have that. And now, as we said before, we have our MJs. And the way the MJs work is the MJs are plus minus the J's. So basically, you have plus minus whatever the J is. So MJ is going to be negative 1/2 and 1/2, right? So now we have our degenerate states for the N equals 2, L equals 0, ML equals 0, right? Now, let's look at N equals 2. And again, we have N equals 2, L equals 0, N equals 2, L equals 1. I'm going to draw a line here. So it's still N equals 2. All of this is N equals 2. We have L equals 1. Scroll down, okay. And as we said, our MLs is going to be negative 1, 0, and 1. So why don't we do that? ML equals negative 1, 0, 1. So the same thing, we have to look at our degeneracies. So J is going to be L, which is 1 plus 1/2. So it's going to be 3 over 2. And J is going to be L, which is 1 minus 1/2, which is 1 over 2. So we did our plus, we did our minus. We've got what we need to do to get our J. None of them are negative. So that's the conclusion of our J's. MJ is going to be plus or minus that. So we're going to have, I'll start with the bottom one first. MJ equals negative 1/2. MJ equals 1/2. So that's our J states for the N equals 2, L equals 1, J equals 1/2. And we have our J equals 3 over 2. So we have to do the same thing again. And I think I'm missing a step. Let me see if I make sure I'm not missing a step here. Nope, that was good. I guess I just got better at doing this. So, and let me make a clarification, by the way. I was looking at just that one. When I say the MJs is to plus or minus J, that is going to be negative J plus negative J plus 1, all of, and leave myself enough room. Let me write it as J plus, let me just do this. Y'all see what I mean in a second. Boom. So the mj is going to be the whole range. In other words, this one is j equals 3 over 2. So it's going to be mj equals negative 3 over 2. mj equals negative 1 over 2. mj equals 1 over 2. And mj equals 3 over 2. So now I have all of the j's in the range of my, all the mj's in the range of my j equals 3 over 2. So basically I make this negative, I add 1, I add 1, I add 1, but I can't be bigger than what j is. So it's always going to be within the range of j. And that's why I have the negative j on this end and the positive j on that end. And you have everything in the middle adding a 1 along the way. So I think I was clear about that at first, because I had an oversight there myself. All right, so now we have all the MJ states for the n equals 2, L equals 1, and all of the relevant MJ states, ML states. And we got all J's from the L and the S. So that's everything. So what this means is that, and let me write this part a bit better to keep the same iteration. All right, so this means that for the n equals 2 state, there's 8 degenerate states, because again, the n is what gives us the energy. So that means that there is 8 states with the same energy according to how the subatomic components of the particles interact with each other. Right? If you have an L0, and L equals 0, J equals 1/2, then you have 2 different ways to have the MJ, and those are 2, but they still have the same energy of the N state, and so on and so forth. So these are eightfold degeneracy for the N equals 2 state. And let me take a look and make sure I didn't make an error somewhere. But I believe I did everything properly. All right, I believe that's the case. All right, so we have an 8 degenerate state. Now, the next thing I'll show you is how we use the Born table to get the actual states. It's kind of hard to see, but if we're going to actually get the states of, like the state to actually get the probabilities of finding the particle at a certain place in the, if I want to find out where is the electron most likely to be given this energy, like where is it going to be distance away from the nucleus of the atom, let's say. You need to be able to get the actual states to take the probabilities of that. So let me find that detail in my notes and let me know if you have any questions, those who are watching. So the way we will start this process is I would say, so I have these 8 degenerate states. Now I write them something like this. One of my states, I'll call this state 1. We have N, L, J, and MJ. And the states in quantum mechanics is written like this. This means like this is a state. So this would be called basically a ket, the way this is angled. And a bra would look like this. So you put these together and you end up having a state that you can actually get probabilities with. Or you can put an observable up in this, let's say the position, and get a most likely position with the bra and a ket. So we're starting to angle towards actually getting stuff in quantum mechanics with this stuff. So now I can plug this in, and I know one of them is going to be N equals 2, L equals 0, J equals 1/2, and MJ, let's say, is negative 1/2, right? That's one of them. We can write another one in which J will be positive 1/2, right? Which is the degeneracies. And we'll call this 2. And what I'm going to do is actually find one or write one real fast so that I can use this Klepp-Gordon table on. And I'll explain what that is. So to remind myself, and actually to let you all know as well what this table means. So basically, and I'll work with this table here. This is the overall L of the particle. This is the overall S, which we talked about earlier. These numbers here in this column is going to be the J of the particle and the MJ of the particle. And these numbers on the side here are going to be the ML of the particle and the MS of the particle. So basically what this does is it allows us to take the values for the coupled state and separate them back into the specific configurations that made this overall state. So here we were looking at the degeneracies of these overall states, but it's hard to tell, how exactly did the L and the S mix up to make this J state. Well, these Klepp-Gordon tables, and we had to actually calculate this stuff by hand in the first class. It's ugly. It's very ugly. But you got to learn how to do it to do it. Even though I probably couldn't do it off the top of my head right now if I tried. But I know how to do it in the back of my mind. But after you know how to do it, you know, they, these states are, I mean, it is quantum particles. They have certain states with certain energies. So they put these in tables. So now if you know how to read this table, you could just look at the table and write the states down instead of actually having to calculate everything and over again. But I'm gonna make a video like that in the future. I'm going to have to learn redo it again in graduate school because you have to actually show that you understand all the graduate level stuff like off the back of your hand. So we're going to have to go through it again and it'll be torture a little bit, but a fun kind of torture. Okay. So what I'm going to do is I'm going to find the L1 and S1/2 and write that one out for my notes, and then we'll look at the Klepp-Gordon table for it. So I'll also look at that one. I wrote that down as, so I'm going to do what again? L1S1/2. I think I wrote that as 3. So L, so this is again NLJMJ. We have N equals 2, L equals 1, J equals 1/2, and MJ of either 1/2 or with negative 1/2. And it looks like I wrote that correctly. Believe so. Okay. So what I'm going to do is I'm going to copy this part of the table out right here. And we'll see if with the help of my notes, I can work this out for you all. And then that should be the end of the science hour. All right. So if I wanted to write the state, now remember, all of these numbers here, you can see how there's these 3/2s, the MJ states. And see here the 3/2 MJ states. We have the J states here, 3/2. You can see how these numbers are dotted around, right? The J here around the table. And So if I wanted, let's say, the J state where the J is 3 over 2 and the MJ is 3 over 2. This would end up being one state. The coefficient is 1. And it would have a ML of 1 and an MS of 1/2. So you have a 100% probability if you have a J of 3 over 2 and an MJ of 3 over 2, you have a 100% probability that you're going to have a state of the particle where the ML is 1 and the MS is 1/2, and of course is a atom, an electron, or something with a 1/2 spin, so that's going to be the case. So if I look at this, ML, MS, 3 halves, I can see that right here. I can see my J, MJ, 3 half, 3 half, and I can see that I have a ML. Did I skip doing my, no, I skipped doing my MS, this is what I skipped. So we know that the spin is 1/2. So the MS is going to be negative 1/2 to 1/2 is how the MS's work. So I know the spin is going to be 1/2 for all of these particles. So then I could end up having a 1 for, did I pick the right one? For ML. Yep, here it is right here. So there's my 1 for my ML, and there's my, let me keep the same color configuration. So this is how these things mix up to make this state. And now you can actually use this, and of course it's not so exciting because it's 100% probability when you have this configuration as far as how the states go, but there you go. Now, let's say I wanted to have my state to get probabilities of, let's say, a J of 3 over 2 and a MJ of 1/2 of the overall state. So what micro parts of the subatomic particle goes together to make that? And actually, let me write this in a different color to make sure I don't confuse myself as well. So now I'm looking here. So I'm going to say the coefficient is going to be square root of 1 over 3. All these coefficients have a square root to it. And this is going to give me a ML of 1 and an MS of negative 1/2. Oh, this meant to be a 2 right there. Right? Plus, I have my other coefficient of square root of 2 over 3, which is here. And this is going to give me a ML of 0 and an MS of 1/2. So now I can see, let's say I wanted to know the probability that I will have this configuration. Well, this number here in front is the probability. So all I have to do is square this number, square it, and I get 1/3. So basically 1/3 of the time you'll see this configuration compared to this configuration, just the way that all the quantum particles and everything work out. And again, these are just like quantum particles. They are what they are. You know, any hydrogen atom that you find in this state, I mean, every single one, you can't distinguish them from each other, and every single one that has this particular configuration, they match this, it all adds up. Let's see if we can find this up here. So I said J is 3 over 2, MJ is 1/2. So I'm still with my J equals 3 over 2, MJ 1/2. So now I'm dealing with this MJ here. and my ML is 1, MS is -1/2. So this is still 1 here, except now this has a negative. So this is how these get together to make that particular state that's happening in reality. And you can see how this goes. And I can do this for every single coupling of these different macro states. And this gives me the actual ways in nature that an L and S particle will intermingle, and it'll give you all the actual states in reality that equals up to all the different degeneracies that comes about, right? And again, you can actually take this and get probabilities out of out of things, but that'll be a whole nother video. So that's the overview. We're about 13 minutes left. And what I'll do is next time I'll come back, and I don't even know if I'll be able to understand it enough tomorrow to do it tomorrow, but I'll try. What I plan to do is I'll come back and actually show you all how the when you actually input the magnetic field with these states, how to get the energies uh, of the Zeeman effect. So as we said before, these energies are the same before the magnetic field. They just look different. The way the spins and everything are mixed up together is different, but it still has the same energy overall. But when you add that magnetic field, as you can see, the MLs are different, the Ls are different. So the magnetic moments of everything is different. So they're going to split differently. So now you end up having several different energy levels. And there's a lot of interesting things that people who really like that stuff, like particle physicists, do with those degenerate states when they split and make a lot of things happen. So, any questions, any comments, anything I can clarify before I close up for the night? Yeah, this is the type of stuff I normally do on my STEM channel. Catherine had asked about this, and technically she did ask on the STEM channel. But I know more people come to this channel, so I figured I would go ahead and do it here. But it is like some more, definitely more complicated stuff, and probably more involved than I normally do. I normally do like an overview of stuff, but be able to see how it really works. And you know, when when particle physicists are doing what they do, and they're trying to find another, you know, configuration of molecules or uh, the stuff they do, you know, I was going to go either into particle physics, or I like either to get into the stuff that's really, really huge, like stars and stuff, galaxies and supernovas, or stuff that's really, really small. And comparing it to, I'm like you, I'm like, dude, I don't know if I could. Look, I'm hanging on by a thread myself. I'm actually doing well in the class, but it is a lot of work, and so yeah, yeah, it's difficult stuff. So technically, it's still beyond mine because I'm learning it right now. This is like the cusp of what I'm learning with quantum mechanics, and and I got to take the graduate level. We gotta do it. So that's one of the classes. Did I sign up for it? To let y'all know real fast. And I'm still gonna do that review, by the way. I think in June, probably because I want to make sure I finish everything. I mean, there is a possibility that I fail the class still. It doesn't. I mean, I'm not close at the moment, but still, you never know. I want to make sure I complete everything. I already finished my relativity class, so that class is finished. I finished my assignments early, so I know I have an A out of that class. Uh, right now, off the top of my head, I have like a B in quantum, A in building scientific apparatus, and I always seem to forget one class. What was my other class? Oh, thermodynamics. I have a B in thermodynamics. So technically, I have right now two A's and two B's. But that can change. I don't think it will, but I'll do my best to make it not. But let me pull up and I'll let you know what classes I'm taking in the last final minutes. The classes that I'm registered for, put it that way, in graduate school. Let's see. Um, and I think I tried to avoid quantum actually because I know I'm gonna have to do a lot more self study for it. Okay, so yep, quantum one. That's what they have available. So I'm taking graduate level quantum one, graduate level stellar astrophysics, and graduate level classical mechanics. So ironically, you end up taking the same classes over again a lot of times, but it just ends up being next level, next level. Like I took undergraduate level classical mechanics, and there's just a whole lot of stuff in high school that you don't realize they just simplify, and then you're like, oh my gosh, all of that's going on too. So that's what it's going to be like. So over the summer, I'm going to have studies. Oh, in the last class, I mentioned how in graduate school you have to like show that you understand the graduate level stuff. So we have to take this class called Foundation of Physics, and believe it or not, it's like all of undergraduate physics in one semester, and we have a test every week. So it's like, do you understand classical mechanics? You know, you have to do that. Lisa says, I appreciate that you're walking us through it. Understanding it is not too probable. And keep up the good work. Thank you. I appreciate it. So I'm glad you enjoyed. Thanks for dropping the line, Lisa. And everybody else who's watching, who watched, thank you all for passing through. Like, subscribe if you haven't. Help me get to 1,000 subscribers. And the plan is to come back tomorrow to show the actual Zeeman energies. But the fact is, I still have to relearn it again. So it may not actually be tomorrow, but I'll try because I have to understand this stuff for my exam, which is Monday of next week. But not next week, but the week after. Monday, 2 weeks from now. So yes, it's a learning curve to relearn and to get clarification because I gotta do well in this final because I did horrible on the second exam. But again, my homework and everything else is good enough where it'll be like extremely hard for me to fail. I like to have make negative points, but still don't want to do well. So at least I'll see y'all tomorrow if I'm here tomorrow. If not on this, I'll probably be on with something. Definitely. And by the way, next week, Saturday is my thermal exam. So I won't be on next Saturday, but I may move that one to Sunday. But Saturday, the 3rd, I'm actually in my thermal exam. So I won't be here next Saturday at the proper time. All right, y'all. Have a good evening. See y'all next time.